Welcome to another session of our reading group. Today we are going to look at properties and quantities. So essentially how we start labeling all the elements that are distinguishable using experimental and verifiable statements. So let me, as usual, share the link in the chat and share the text. Let's see more, share, there it is, and properties and quantities, and we can jump right into it.
Okay. Chapter 3, Properties and Quantities. In this chapter, we will introduce the idea of properties, which we use to label the possibilities of an experimental domain. For example, we may use names to distinguish among people, fur color to distinguish among cats, pressure to distinguish the state of gas. In particular, we'll define a quantity as a property that has a magnitude. We can compare two different values and determine which one is greater or smaller. Continue. Okay. Instead of simply assuming we have quantities, we will need to construct them from the verifiable statements of an experimental domain. To do that, we will prove three theorems that will give necessary and sufficient conditions for that construction, clarifying how quantities are defined experimentally. These theorems will allow us to understand how the ordering of these values for a quantity are linked to the logical relationships between the verifiable statements, and in particular, how the ordering of values is linked to the ordering defined by narrowness. After characterizing quantities in general, we will see the cases of discrete and continuous quantities. We will see how discrete quantities are linked to decidability, the ability to verify both the statement and its negation, while continuous quantities are linked to a lack thereof. We will then discuss how the requirements for continuous quantities cannot be truly realized in practice and what happens when that idealization fails.
Right, so we are basically going to, so really the distinguishing thing between quantities that we can put an ordering and then we can say that something's greater than something else. That's basically going to be the difference. And then the idea is that we're going to basically derive the necessary and sufficient condition for having real numbers connected to experimental verification, so that we would know exactly when in physics we assume that we have real numbers, what are the assumptions that are baked into that decision.
Okay, is it my turn?
Yep.
Sorry, I couldn't hear anything for the first few minutes, but it's fixed. Okay. Properties. Whether the result of direct observation or not, a physical object is most often identified by its properties and their values. A person may be identified by a name and date of birth. A bird may be characterized by the color of its beak. The state of a particle may be qualified by its position and momentum. In this section, we define how in general we can use properties to label the possibilities of an experimental domain. Each property will specify a continuous function from the possibilities to the topological space of the possible property values. Some properties may fully identify each possibility as they assign distinct values, and some may also fully characterize which statements are verifiable. Just one question. The possibilities are a subset of, well, all statements. And they have just a subset topology.
No, the possibilities are the set of cases that the verifiable statement can distinguish within a domain. So, for example, all the possible values of position and momentums are possibility of the domain of a classical the state for a classical system.
Yeah, they are like the individual terms in the min-term kind of thing.
Yes. Yeah.
Yeah. Okay. And they like the topology we're usually talking about is the topology on like all statements.
The topology is the topology on a set of possibilities.
Okay.
So you have experimental domain. For the experimental domain, you get the possibilities, And the verifiable statements are a topology on the possibility.
On top of them. Okay. Yes. Okay, yeah, I got that confused. Those are the points on top of them is obviously defined topology. Okay, it is the
Yeah.
same topology we're talking about all the time.
And so the
But
property may fully identify each possibility, as we'll see, meaning that for each possibility you have a unique set of properties. But that doesn't mean
yeah,
that the properties might tell you which statements are verifiable or not. So
yes.
then there is this extra step that you have to identify which are the possible statements that are actually verifiable, which means characterize the topology. And so if you have a set of, now you can have a set of properties that not only characterize the points, the possibilities, but also characterize the topology.
Yep. Okay. Yeah, maybe one more paragraph. Okay, suppose dx is a domain for animal identification and x, its possibilities are all animal species. Providing good names and definitions for a species is a whole scientific subject by itself, i.e. taxonomy, with its own rules, the International Code of Zoological Nomenclature. The ICZN assigns each species a name composed of two Latin words. For example, Passer domesticus is the official name for the house sparrow, while Passer italia is the one for the Italian sparrow. This means that identifying an animal species is equivalent to identifying its name. Therefore, the domain to identify the species name, DQ, is equivalent to the one for identifying the actual species, and we have an experimental relationship Q from X to Q between them. As each species is given a unique name, this is the most discriminating type of property, one that covers the whole range of possibilities and fully identifies each of them. But this is a special case.
The ICZN also assigns a genus, or in plural, genera, to each species, which corresponds to the first part of that species name. For example, both aforementioned sparrows are of the genus Passer, while all swans, black or white, are of the genus Cygnus. Now suppose that Q is the set of all names for all genera, and little q from x to q is the function that gives us the genus name for each species. We can still use this as a label for our possibilities, but it does not fully identify them. On a different note, we could decide to distinguish species by their morphological attributes. For example, if Q is the set of all colors, we can imagine a function that gives us the beak color for each species. The function is partial, not defined on all elements, as not all species have a beak or its color may not be unique. We have little q from U to Q, where U is a subset of X, is the set where the property is defined. To be consistent, though, we must at least be able to tell in what cases the property is actually defined. For example, we must be able to tell whether an animal has a beak. Therefore, there must be a verifiable statement that is true if and only if the property is well defined. The set U then must correspond to the verifiable set of said statement. Other examples of properties include the postal address for buildings, tax ID numbers for people, generation for fundamental particles, position of the center of mass of a body. In all these cases, the general pattern is that we assign a label to a possibility from an established set.
A property for an experimental domain dx is any attribute we can use to distinguish between its possibilities. Formally, it is a tuple, QP, where Q is a topological space and lowercase q from U into that Q is a continuous function, where U is an element of Tx. It's a verifiable set of possibilities. Justification. Suppose Q is a physical property that can be assigned to distinguish the set of possibilities U and X. We must be able to tell experimentally whether the property is defined for each possibility. Therefore, we are justified to assume that U is a verifiable set. Let Q be the set of possible values for the property. Each element of U will be matched with a possible value. Therefore, we are justified to assume that there is a function Q from U into Q that specifies that mapping. As we must be able to experimentally distinguish between the values in Q, there must be a collection TQ of verifiable sets that correspond to the possible verifiable statements associated to the quantity. Therefore, we are justified to assume Q is a topological space. Moreover, since the property value is determined by each possibility, the function Q establishes a causal relationship between the two, and therefore we are justified to assume Q is a continuous function.
Right, so basically reusing everything that we used before to say that if we have a property that is really determined by the possibility, then and we can go and tell that property is something that we go ahead and verify experimentally, then we have a continuous map from one thing to the other.
Okay, so we pick Q is like a label space or some property space.
Yeah,
Sample
Q is
space.
the property.
Okay, and then it's only defined on an open set, like some possible like a subset.
Yeah.
Okay.
Right.
But
And
it
so
is
this is basically the structure then you could think of using for a manifold, right? You have a manifold which is the set of all the points that you want to distinguish, and then you have your coordinates that are only locally defined. What does it mean that are locally defined? It means that that property is not defined over the whole space.
Yeah.
Right? But this is generalized so that we don't just talk about numbers, we can talk about anything that we want.
Yep. Okay.
Okay. All right. Note that we have not defined a property as an experimental domain. The possibility of the domain for a property would be a statement like the species name for this animal is Passer domesticus, while the value is just the object, Passer domesticus. The idea is that the property and its values are defined independently of the particular object. For example, distance in meters is defined independently of whether we later want to measure the Earth diameter or its distance to the moon. There's a footnote there. While in principle we could envision a formal construction of properties and their values purely built on top of the notion of a statement, e.g. define the value red to be the set of all statements that claim that something is of that color, we're not going to do so. While appealing in some respects, it's not clear whether such a construction would actually help to clarify the underlying assumptions, while it is clear it would distract from other more critical issues. Yeah, that seems fair. The fact that the property and its values are defined more generally leads to some subtle issues. Even if each possibility of the domain corresponds to one property value and each verifiable statement of the property is equivalent to a verifiable statement of the domain, the reverse may not be true. Consider the experimental domain for identifying negatively charged fundamental particles. In this case, each particle will correspond to a unique value of mass, and by measuring the mass, we can infer the particle. But for each possible value of mass, we will not have a possible fundamental particle. Moreover, the verifiable statement, this particle is an electron, would correspond to an infinitely precise statement of the form, the mass of the particle is exactly this electron volts, which is not verifiable. The reason is that identifying a negatively charged particle is not the same as measuring its mass with arbitrary precision. In the first case, we can stop when there is only one possible particle within the finite range of our measurement. Now consider the experimental domain for the position of the center of mass of a particle along a particular direction. Not only is the distance from a fixed point enough to identify the position, but for each value of the distance, we also have a possible position of the particle. We say that a property fully characterizes an experimental domain if each possible value of a property corresponds to a possibility of the domain, like in the case of the distance from a reference and a position of the particle. The idea is that it tells us what cases are possible and how they are experimentally verified. Instead, we say that a property fully identifies an experimental domain if each possibility corresponds to a unique value, like in the case of a mass of a negatively charged particle. The idea is that the value of the property allows us to uniquely identify the possibility, but nothing more.
Okay, is it clear the difference?
Yeah, I mean it's like the difference between surjection and bijection in some way. Well, not quite, but it's like the difference between a well, I guess it's the difference between like a partial and a or the it's the difference between having an example of each value or not. Like if you're the fully characterizes when like they're every uh wait, do I understand this?
Exactly, like it's subtle.
It's
Like
like
it took me some time to even figure out that the two different things were different. So
so it's the difference is that the for fully characterizes every like numbers for instance has a possibility. Like there's a possibility for each number. For
yeah,
uniquely characterizes we don't have that. Like the difference is that it's like almost injective for every if you know the number then you know the thing, but
yeah,
you also aren't guaranteed to be able to go back or
yeah.
you yeah.
And then there's also going to be an issue on the topology when you go back, that it's not going to be exactly the same thing.
Mhm. Okay. That is a little subtle. Yeah.
Right. So it's interesting to me, especially when you do a particular identification, because you are effectively going from something that is in principle continuous, but then the map is to something discrete, and that's where sort of topologically things change very abruptly, and you can't really have like maps that go back and forth. And in some sense, it's also when you are in quantum, right, and you basically go from something like the block ball, where there is a continuum between all the points, but then you say I only measure one particular observables and only spin up and spin down, then you are mapping from something continuous to something discrete, and that's also similarly you can't go back. So there are a lot of issues like that that are subtle, and so like it's but the point is here that you can find these issues anywhere if you look for them. And so I think the two definitions are the things that sort of make it clear to me. So you are fully identified by a property if its value is enough to uniquely determine the property. And so when you have your Q, your Q, big Q and small q, then the possibilities are fully identified if this map is injective. And this is not really telling you, you just have a continuous map that it's injective, but fully characterized means that the map is a homomorphism. Not only you can go back and forth, but the topology is also conserved.
Injectivity and homeomorphism make more sense to me. That's a good like way to latch onto it.
Yeah, exactly. Once you have the clear problem physically, then you can find the mathematical characterization, and then the mathematicalization helps you to make the physical concept more stable. This is when you can do these things properly, you sort of both sides help each other.
Yeah.
Okay, so there is a question from the chat, so let me go through it. I'm concerned about the statement the mass of the photon is zero. Hypothetically, we make a measurement of the mass and find it is very close to zero, maybe 10 to the minus 20. This becomes evidence to claim that an alternative statement for photon mass is less than 10 to the minus 20 becomes correct with something like 0.999 Bayes in support, but an alternative statement. But I'm thinking the theories function differently when making experimental. We aren't trying to justify the statement photon mass is zero or 10 to the minus 20. That's not the statement we care about. The statement we care about is the one all statements in this list are correct within 100%. Then we imagine that all statements on the list are like photon of mass zero. So the idea is that when we measure something, we never measure the infinitesimal, the infinitely precise value. So if we make a measurement of the mass of the photon, will be something like the mass of the photon is less than 10 to the minus 13 eV, something like that. And that corresponds to an open set. And then every possible statement inside is something that can be true, and you don't know which one. So that's basically how it works. So we'll continue, and then we'll see if because the chat is slow to update. So let's continue, and if there is if that didn't solve the problem, I can go back to it again.
But can I maybe check the example that you gave, where you start with a mass and you want to just identify a particle, so you know there are like finally many possibilities. So you would start with a mass, like if that's the property, what would be the map here? Would we do something like, I don't know, the closest mass that we know exists? So you would measure a mass, and that map would tell you, well, it's closest to electron mass, so we would identify it as an electron or something like that. And because I understand, like if you would have a range, you would say if it's in that range, I can verify.
Right. So what you have is that fortunately, the spectrum of particle masses and charges is discrete, and the value are far enough from each other that even if we don't know the perfect value, we can distinguish between them. Right.
Yeah.
So we are able to restrict the value of mass and the value of charge enough such that when they come in a detector, you can say, aha, that's an electron.
Yeah.
Right? And sort of conceptually, you have a space of possible particles, which is going to be a discrete space because it can be an electron, a muon, and so on. You can count them, right? And then you have, let's say, the value of mass, which is a continuum. And then so your big Q is R, and then your small q takes a particle and gives you the value of the mass in the spectrum. And so as long as you have an open set on the mass, which is that corresponds to a verifiable statement, that only contains one possible value of the mass of a particle, then you're able to conclude, aha, I have that particular particle. And then you're done.
Okay, I didn't take that serious enough. It is important that the map goes backwards, kind of.
It's always, as we saw the other time, the causal relationship goes forward, so from the particle to the value of mass, but the inference relationship goes backwards from the mass to the particle.
Okay,
Actually, from the open set on the mass to an open set of the particle.
Okay. So in that case, if we had, well, I guess charge and mass and spin and maybe more, then we would have, they would fully identify.
Yeah.
That we would have an injective map.
Yeah.
Okay. So the Q would have to be this list of some numbers. Okay.
Yeah.
But it would not be fully characterized because we go into continuous space that won't be invertible in a continuous way.
Right.
Okay.
Because the point is that the way that you measure the mass is not exactly the same way that you measure and identify particles.
Yeah.
Like the open sets and therefore the verifiable statements that you have on mass are significantly different from the statements on the particle. The statements on the particle are, this is an electron, this is not an electron, this is a charged particle, this is not a charged particle, right? And they're all decidable because either you have one or another, you can actually verify all of them. But the statements that you have on the mass are not at all like that, because you can't say that I have an infinite precision statement, you can't identify all the points, you have a continuum, so yeah, it's completely different.
Okay, no, that makes a lot of sense.
Let's see from the chat. Okay, so he's gonna digest that. Okay, let's continue.
We now focus our attention on those properties that can be quantified. The number of people in a group can be quantified by an integer. The distance between two objects can be quantified in meters. The force acting on a body can be quantified by the magnitude of a vector expressed in newtons. The defining characteristic for a quantity is that a value can be greater, smaller, or equal to another. Okay, for a vector, I will have to pick a direction, but okay.
Yeah, so the vector is a quantity because it has a norm. If you don't have a norm, the vector is basically not a quantity.
Okay, in that sense. Okay, yeah.
Yeah. It
In
could
the
be a set
section,
of quantities, right? Then you're still fine. It's a set of quantity, but then you're comparing one, each of them by themselves. So you have position and momentum, right? Position and momentum is not a vector quantity in the sense that there is no norm, there is no, but it's a set of quantities. You can go and compare each of them individually.
yeah. In this section, we will define a quantity as a property with a linear order, which we assume given a priori, and study its relationship with the experimental domain. We will define the order topology, which assumes one can experimentally verify whether a value is before or after another one. We will assume that a domain is fully characterized by a quantity only if the possibilities themselves can be ordered, and how this ordering in the end is uniquely characterized by statement narrowness. 10 is less than 42 because the quantity is less than 10 is narrower than the quantity is less than 42. Okay.
So that's going to be the important bit, that the ordering structure between these values is exactly the ordering structure that we have between statements through narrowness.
So this will naturally just give us the topology of the real numbers, right? Well, I mean, the topology, whatever subset of the real numbers or values can take on.
Yeah. And also the natural topology of the integer, of the rationals, everything that has an order. Yeah.
And just to be clear, what linear order, what does that mean? Does it would the norm define a linear order on a vector space that is not like one-dimensional?
Yes.
Okay, good.
But it's not, so in that case, it's not an order in the sense that the order is on the equivalence classes, right? You will have, to have an order, if you can have two elements at the same position.
Okay, so on the vectors themselves in 2 dimensions, let's say, there would not be an order. But then, of course, I just put them in the equivalence class of the same radius, and then by
Correct.
construction, I will have an order. Okay.
Yeah. It's the order
So,
on the norm, not the order on the vectors. The vectors themselves are not ordered.
okay, yeah, that's what I thought. Good.
Okay. Yes, as the defining characteristic for a quantity, or as the defining characteristic for a quantity is the ability to compare its values, then the values must be ordered in some fashion from smaller to greater. Therefore, given two different values, one must be before the other. Mathematically, we call this we call linear order an order with such a characteristic as we can imagine the elements positioned along a line. Yes, okay, this is called a linear order. Note that vectors are not linearly ordered. No direction is greater than the other. Therefore, in this context, a vector will not strictly be a quantity, but a collection of quantities, which, to be fair, is usually how vectors are defined in the first place. Yeah, footnote. In other languages, there are two words to differentiate quantity as in physical quantity, and as an amount, right? It is the second meaning of quantity that is captured here.
Yeah.
Right. So the idea, I presume, is that a vector is an element of R3, for instance, is just three different numbers that corresponds to like the X, Y, and Z, or whatever basis you want to choose. Right. We also have to define how this order can be experimentally verified. The idea is that we should at least be able to verify that the value of a given quantity is before or after a set value. We take to be equivalent we take to be equivalent to the mass of the electron is more than 510.5 keV, but less than 511.5 keV. And there's a footnote there. This allows us. Oh, sorry, I skipped a line. That explains what that was. Yes, this allows us to construct bounds such as the mass of the electron is 511 plus or minus a half keV, which we take to be equivalent to this statement where we talk about it's more than this value but less than this other value. Yes, okay.
Yeah.
So yeah, sorry. I was like, why did this read weird? Yeah, the sentence, the mass of the electron is 511 plus or minus half a keV, could instead be referring to the statistical uncertainty instead of an accuracy bound, and would constitute a different statement when this different meaning is attached. We will be treating these types of statistical statements later in the book, but suffice it to say that they cannot be defined before statements that identify bounds. Yeah.
So this is a particular problem because a lot of people, especially when they try to reconstruct quantum mechanics, they take a probability as a foundational like structure to be able to define measurements. So you say, oh, but whenever I measure something, I define it that it's measured with some statistical uncertainty p and so on, whatever. And the issue is that you can only do that once you have defined the sharp bounds, because the probability needs to be defined on some type of sigma algebra and so on with a set of points. And so it cannot be the initial, like the most fundamental level. Or another way to say it, it's before I say that I measure 35% heads and the remaining tails. You need to know with certainty what tails and heads are, such that you can count them. And so for the single shot measurement, you need to be able to put the value into bins, and then it's the bins that have the probability, not the original value. And so again, we were doing the most basic level, which is we have these bins and we're putting things in the bins, and that's what the measurements are.
Okay, yes. Yeah, for integers, this also allows us to verify particular numbers as the Earth has one natural satellite, which is equivalent to the Earth has more than 0 natural satellites, but fewer than 2. Therefore, we will identify the order topology as the one generated by sets of the type, interval from A to infinity and interval from negative infinity to B.
And these are open intervals.
Mm-hmm. Yes. So a quantity then is an ordered property with the order topology. Right. That seems like a pretty nice way of, yeah.
Of justifying all the math that we standardly use, yes.
Yeah.
That's basically the idea.
It would definitely be harder to start with the statistical Gaussian probabilities and stuff.
Yeah. Yeah, you need this stuff first, because the Gaussian probability is going to be defined on some sigma algebra, which is typically maybe the Borel set and the Lebesgue measure. Where do you get that? Well, you get this from this first.
Okay. A linear order on a set Q is a relationship denoted, well, less or equal, that takes two elements in Q and gives us a Boolean value, such that it's anti-symmetric if Q is less or equal than, if Q1 is less or equal than Q2, Q2 is less or equal to Q1, then they are equal. Transitive, Q1 less or, well, smaller than Q2, Q2 smaller than Q3, Q1 is smaller than Q3, I guess. And then total, they are, okay, it's a total order. I can either relate it in this way or this way.
Yeah. One of them has to come before the other.
Yes. A set together with a linear order is called a linearly ordered set. So we define this to be a linear ordered set, Q with a relation. Then the order topology is a topology generated by the collections of sets of the form open interval a to infinity, which is defined as all elements in Q that are bigger than A, which I assume we literally define as not equal, but A smaller or equal to Q.
So
I
this is strictly strictly greater, so we have removed the equal.
Yes. Yes. Okay, and then the other way around for the other interval,
Yeah,
and that's our basis for the topology. Okay,
yeah,
that's
that's
quite
basically it.
intuitive. A quantity for an experimental domain, dx is a linearly ordered property. That's okay, definition, yes. Formally, it is a tuple where we just add the relation to the space.
Yeah,
And then, yeah, without that, it's a property as usual. And then that's a linear order. Then it's a topological space with the order topology. And that is the topology in which this map Q has to be continuous, I guess.
yeah.
Good. Yeah, that makes a lot of sense. As for properties, the quantity values are just symbols used to label the different cases. The set Q may correspond to the integers, real numbers, or a set of words ordered alphabetically. There's a footnote. When consulting the dictionary, we use the fact that we can experimentally tell whether the word we're looking for is before or after the one we randomly selected. The units are not captured by the numbers themselves. They are captured by the function Q that allows us to map statements to numbers and vice versa.
Right. So it's if I have the position of a particle, right, and then I want to know the position from a particular the distance from a particular point in meters or in kilometers, I'll be using different functions.
As we want to understand quantities better, we concentrate on those experimental domains that are fully characterized by a quantity. For example, the domain for the mass of a system will be fully characterized by a real number greater than or equal to 0. Each possibility will be identified by a number which will correspond to the mass expressed in a particular unit, say in kilograms. Sorry, I was trying to make sure I hadn't skipped a line again. As the values of the mass are ordered, we can also say that the possibilities themselves are ordered. That is, the mass of the system is 1 kilogram precedes the mass of the system is 2 kilograms. This ordering of the possibilities will be linked to the natural topology as the mass of the system is less than 2 kilograms. The disjunction of all possibilities that come before a particular possibility is a verifiable statement precisely because it corresponds to a continuous interval of the linear order. Right. We call a natural order for the yes, we call the natural order for the possibility a linear order on them, such that the order topology is the natural topology. An experimental domain is fully characterized by a quantity if and only if it is naturally ordered and that quantity is ordered in the same way. It is order isomorphic. In other words, we can only assign a quantity to an experimental domain if it already has a natural ordering of the same type. All right, I guess I can read these definitions. Let dx be an experimental domain and x its possibilities. We say less than or equal to is a natural order for the possibilities of the domain if the order topology constructed from that ordering coincides with the natural topology. We say the domain and the possibilities are naturally ordered if they admit a natural order. All right, yeah. And then similarly, so you have two ordered sets. A function between them is increasing if for every Q1 and Q2 in the first set, Q1 is less than or equal to Q2, it implies that their images under that function f are ordered the same way. It is an order isomorphism if it is bijective, and for every Q1 and Q2 in Q, Q1 is less than or equal to Q2 if and only if f of Q1 is less than or equal to f of Q2. Yeah. Okay.
Okay, so this is the standard thing, like increasing, you can go from one order set to the other order set, and you keep the ordering, and it's an isomorphism, you can go back and forth, and you still keep the ordering in both ways.
So you change from implies to if and only if. Is there a case where that those aren't the same?
I think so. And it's one of those details of order theories that I would have to go back and look. But I think that the fact that you have a bijection that it's increasing, I don't think it's necessarily an ordered isomorphism.
Okay.
Yeah, on a real line, you would always have like if it's monotonically increasing, you can invert it, and then it will be still the same. But I guess that it might be specific to the set.
Oh, for example, a simple thing, even in the real line, you take all the numbers and you map them to the same element. Oh no,
Mhm.
but then it's not a bijection. Sorry. No, okay. I don't have an example right now. I would have to go and relook my notes on order theory.
Yeah, I don't know. It feels like it should be like every bijective increasing function is, well, I guess I don't know if there's a
It could be. I have to go and relook. So let me. I
it's
have a
not.
cheat sheet of order theory. I could go and look if it's. Let's see.
I suppose it's not particularly important since the if and only if there certainly means what you want it to mean. I'm just nitpicking about.
Yeah. It's. I don't recall whether it's. So definitely, if it has to be an ordered isomorphism, it has to be like that. Like the only thing that I do not know is whether a bijective increasing map is automatically an ordered isomorphism, and it could be, but I would have to go and look at that.
Well, maybe if it's not strictly increasing, right? It could be you could have on the graph map from reals to reals. You could have like a flat section that's still
Yeah, but the
increasing
problem
function, but strict.
is not the. Oh, okay, there you go. You put a different ordering on the reels, but no, because they have to be different. So you can't, like if you have two elements in the same ordering, they have to be different. So it might be that actually if it's bijective just because of the fact that they have to be the same if they're in the same point of the ordering and the ordering is preserved, you're also doing that. Let me see if I have decreasing function, another is more is an invertible embedding a bijective increasing function whose version is increasing. So in the notes that I have, it says that an order isomorphing is a bijective increasing function whose inverse is increasing. I don't have it that all of them are.
Who's
So
inverse?
Yeah,
I
since it's I think
So
it's a bijection, and since it's a total order, like if I want to go back,
yeah, it's because it's
there
a
are
total
exactly two
order.
points. Yeah, there are exactly 2 points, and they
Yeah.
must have some relationship. And then I told
Yeah.
you before, it has to be preserved. So
Okay, it's because yes. Okay, so if it's a total order, it will become, but it might not be a total order, and then you're not guaranteed. That's
yes,
gonna be the
oh,
case.
okay.
So this definition here, they
Well,
are not implying that the ordering is total, right?
right. Okay. Yes, this is just a
uh,
more statement. That makes sense.
Okay,
Okay.
we got it.
Um, right. Which even if we aren't using partial orderings, that's yeah,
Yeah.
good to have. All right. Yeah, and theorem 3.9, property ordering theorem. An experimental domain dx is fully characterized by a quantity a triple q less than or equal to a little q, if and only if it is naturally ordered and the possibilities are order isomorphic to the quantity.
Okay, so basically what happens without looking at the proof is that so you have a bijection and you need to preserve the topology between one and the other, but the topology is the order topology in both cases. So preserving the order topology means preserving the order itself.
But did we start, or we use the property itself to order the possibilities, right? So in
Yes.
that sense, we also have now an order
Yeah.
on that because due to that function.
Yeah.
Q.
You can go back and forth because of that. Like if you start
Yes.
with the experimental domain and you know that you are fully characterized, and you can bring the topology on the other side. If you start with
Okay.
let's see what's going to be a good place to stop, because then at some point it becomes unwieldy. Yeah, okay. Maybe we can see if we can go up to the references.
Okay. That's just the end of the proof. Okay, now
Okay.
that we have established that the linear ordering is something already present in the domain, we can show it is actually based on the ordering of verifiable statements in terms of narrowness. That is, the mass of the system is 1 kilogram is before the mass of the system is 2 kilograms, precisely because the mass of the system is less than 1 kilogram is narrower than the mass of the system is less than 2 kilograms. The set of statements on B of the form the mass of the system is less than Q1 kilograms are linearly ordered by narrowness. And their ordering is the same as the ordering of the possibilities / values. Similarly, the set of statements BA of the form the mass of the system is more than Q1 kilograms is also ordered by narrowness, but with the reverse ordering of the possibilities of values. These are the very statements whose verifiable sets define the order topology and therefore jointly constitute the basis for the experimental domain. Okay, now consider the statement S1. The mass of the system is less than or equal to 1 kilogram. With S2, the mass of the system is less than 1 kilogram. We have that S2 is narrower than S1 because we excluded the equality. Okay. In fact, if we replace the value in S2 with anything less than 1 kilogram, we'll still have that it's narrower than S1. Yeah. Instead, if we use a value greater than 1 kilogram, we will have the opposite relationship. In other words, if we call B the set that includes both the less than or equal and less than statements, this is also linearly ordered by narrowness. But the mass of the system is less than or equal to 1 kilogram is equivalent to the negation of the mass of the system is greater than 1 kilogram. In other words, B as the union of all statements of type B, which is everything less or equal, I think, union with like negation of all the other ones, contains all statements like the mass of the system is less than Q1 kilogram and not the mass of the system is more than Q1 kilogram. And these are all linearly ordered by narrowness.
Okay, that makes sense.
Yeah.
But by the way, this small b is for before and this small a is for after. So that's how you distinguish it. That's why I chose before and after, because I make a nice.
Mhm. Right. The ordering of B can be further characterized. Note that S1 equals the mass of the system is less than or equal to 1 kilogram is the immediate successor of S2, the mass of the system is less than 1 kilogram. That is, they are different, and there can't be any other statement in B that is broader than S2 but narrower than S1, since they only differ for a single case. This will happen for any mass value. So B is composed of two exact copies of the ordering of X, where each element of one copy is immediately followed by an element of the other copy. Moreover, if a statement in B has an immediate successor, then there can only be one case that separates the two. If we call Q1 the value of that case, then the statement must be of the form the mass of the system is less than Q1 kilograms, while its immediate successor is of the form the mass of the system is less than or equal to Q1 kilograms. The successor is broader by just the possibility associated with Q1. Therefore, statements in B that have an immediate successor must be in B before as well. The main result is that the above characterization of the basis of the domain is necessary and sufficient to order the possibilities. If an experimental domain has a basis composed of two parts, B sub B and B sub A, such that B is equal to the union of B sub B and the negation of B sub A, and is linearly ordered by narrowness with those characteristics, then the experimental domain is naturally ordered. The possibilities can be written as X, or all the possibilities X can be written as not SB, is that and? Not SA, where SB is in our before statements, and not SA is the immediate successor. In fact, the mass of the system is 1 kilogram is equivalent to the mass of the system is not less than 1 kilogram and it's not more than 1 kilogram. Note that because of negation, the possibilities may not in general be verifiable.
So this is the thing that took me some time to figure out, that then it's the property that we use later in the next section to find the necessary and sufficient condition for the ordering real numbers and all that. It's this trick.
Okay, let Bx be a naturally ordered experimental domain and X its possibilities. We define the following notation. X is less than X1 is defined as I forgot, but it's or
Is a disjunction?
disjunction for all X and the possibilities that are less than 1.
Yeah.
So we just take all these statements.
Yeah.
Okay.
So it's basically, if in terms of
Yeah.
sets, we are constructing the sets, but these are not sets anymore. These are statements, and so we're making the disjunction.
I see. Okay.
It's basically we're trying to map these ideas of before and after and the sets to the logical counterpart.
Okay. Yeah. Okay, so all these definitions are very natural. Okay,
Yeah.
that is, they represent statements like the value of the quantity X is less than X1. Okay. Then we have a corollary. Based on the previous notation, less or equal is the negation of greater, and bigger or equal is the negation of smaller. Okay, it's a proof. I assume they're just basic
Yeah, yeah, just
order
keep the
theory.
both of them. Yes,
Okay, good. Definition. Let dx be a naturally ordered experimental domain and X its possibilities. Define B before are all statements for X less than something. And then B after is the other one. We define B as the union of this and the negation of BA. Okay.
So we're basically doing formally all the things that we described before in the text.
I see. Okay. So we defined a basis. All right. B.
Yeah, we're defining a set of states that's the basis because these two elements are going to be bases. Yeah.
Okay. Then we have another definition. Let Q be an ordered set. We take two elements Q1, Q2. Then Q2 is an immediate successor of Q1, and Q is an immediate predecessor of Q2. If there is no element strictly between them in the ordering, that is, Q1 is less than Q2, and there is no other Q that I could put in between. Two elements are consecutive if one is the immediate successor of the other. Okay. Then let dx be a naturally ordered experimental domain. Then all statements of the type something before the other, together with the narrowness relationship, and then same with BA, and then same for this specific union, are linearly ordered sets. Moreover, before with narrowness and after with broadness, I think, are order isomorphic to the possibilities with less or equal. Okay. It said this less or equal that we defined before, essentially.
Yeah, because this is a natural order experimental domain, so the possibility comes with an ordering.
Yeah.
And then you basically say all these statements of this form, they're ordered by narrowness or broadness, and the ordering that they have is ordered isomorphic to this. So you can go from each element of each element of here, preserving the ordering. And also in this case is the same way, right? It's just that the ordering gets swapped.
Yeah. Okay.
That's the proof is gonna be like tedious, but the sort of the result is obvious. And then there is this proposition.
What do we say? Okay, let BB and BA be two sets of verifiable statements such that the basis is like this. It's linearly ordered by narrowness. Let DB and DA be the experimental domains they respectively generate. And then we also define D in the same way, DB union negation of DA. Then DB with narrowness, DA with broadness, and D with narrowness are linearly ordered.
Okay, so now we don't start with knowing what the ordering here is, right? We don't have a domain, we're going to construct it. We just have two sets that are a set of verifiable statements such that if we do the, one with the negation of the other, these are linearly ordered. And then we show that these generate domains, these two domains that are linearly ordered. And then, as again, we're gonna skip the proof, and then there's gonna be the main result, which is this.
Okay, domain ordering theorem. An experimental domain dx is naturally ordered if and only if it is the combination of two experimental domains, dA and dB, such that D is dB union negation of dA is linearly ordered by narrowness. Okay, it's like lowercase d or the normal d is a basis. Oh no, it's just we define it like that, and then
It's not the basis because you have a
we just
negation,
define
right?
it like that and check whether it's linearly ordered by narrowness or not. Okay.
Exactly. Yeah, that's
Okay.
the part about, yeah.
Okay, all elements of D are part of a pair, SB and negation SA, such that, well, SB is in DB, SA is in DA. And the negation is either the immediate successor of SB in D, or SB is already equivalent to the negation of SA. And then if S in D has an immediate successor, then it is in DB. Okay. Successor. Okay.
Okay, so that basically formalizes this idea that the statement before and the statement are not after make these pairs for each element. Right? And so if you're linearly ordered by an arrays, you could have that structure, but you might not have that you have pairs. Right? There are pairs that are immediate successor, that are the consecutive from each other. And then there is still a case in which there is no element in between. So for example, for the rational numbers, the value is before pi and the value is not after pi. Those are the same statements because there is no pi. And the thing is still linearly ordered. So you could have an order that is not complete, meaning that you don't have all these elements inside. And then the other thing that you need is that if one of these elements has an immediate successor, then it must be at least one of the before elements, so that then you can put another afterwards. And once you have this, then through a couple of page and a half, it's not even that, but it's very dense. You can then show, okay, then I have a natural ordering, it comes from an order topology and so on. So what basically this tells you is that the logical relationship of verifiable statements of the type something is before and something is after is enough to characterize the ordering in the domain. And this is what we're going to use later to basically say, okay, when we measure things experimentally, those are the verifiable statements that we have. We have references and we can say, oh, something is before the reference or something is after the reference. And so creating these quantities means saying, oh, I have lots of references and I can measure when stuff are before and after, and then I construct my linear order just for that. And we stop it here, which is a perfect place to stop. So next time is going to be references and constructing the numbers from sort of metrological assumptions of what you can get before and after.
Okay.
If you guys have questions directly on this, otherwise there is a question on the chat on something slightly different, and I'll take that.
I don't have anything
Okay, so we go back before.
right now.
Okay, I'm gonna. Okay, so let's say accelerator is a well-defined quantity or vector. Well, just say that we are in one dimension, so it's a quantity. And let's assume that the mass of the photon is 0. Oh, but then you can't have an accelerator or an acceleration on the motor. Finally, assume acceleration is also a f equals over m. Then if a photon has had forces on them, we go. Hi, Ian. Then if a photon had forces on them, we will go try to calculate acceleration by the mass of the yeah, so acceleration is not defined for photons because photons travel the speed of light, and so you can't accelerate the photon in the sense you can't change the velocity. In principle, you can change direction, and you can kind of see that as an acceleration in the sense that it's acting on the vector and not on the quantity, but even that it's a little bit problematic. So finally, if it acts on photons, it can't be a force because correct. That's why photons and massless objects in general, they experience gravity not as a force, but as this distortion of space-time. Like it's not that they are being pushed around, it's just that the space itself is not flat, and therefore the photon just follows the path that it's given by the space-time not being flat. That was a business of clearing up by the looks of it. Yes, so this, yeah, so the thing that we did today, like, and we're gonna do next time, was probably the hardest bit of thing that I had to figure out, because it's one of those problems where, you want to try to say what are the necessary sufficient conditions of real numbers, but you can't assume that you have an ordering, so you have to you have to figure out what the orders come from. But every time that you write a picture, you have an ordering already in front of you, and so you kind of have to get out of your head to figure out what are the pieces that you need to put in between, and it was like ah. But then I found this trick that we found today that was basically the one of the turning points for me. Okay, so we probably are gonna have like another like 1 or 2 sessions on this, and then we'll have to decide what to do if not reading the book. We might start having just random session where people can just come and talk about whatever they want. That could be a sort of an open office type thing. It might be more interesting for people. If people have ideas, please put in the comment or send me an email so that we can start planning. Anything else? Okay, then let's just stop in here, and thank you everybody for watching, and I'll see you next time. Bye.
All right.
There we go.